conspiracy after conspiracy coming to light.
Our objective is to determine which of the almost limitless options that we can consider best describes our own universe. By demonstrating how the tiniest particles influence everything in our environment, physics is the science that solves the universe's greatest mysteries. Scientists at CERN, the largest particle physics laboratory in the world, are always pushing the envelope of knowledge, leading to groundbreaking discoveries such as the effect of gravity on antimatter and precise measurements of the Higgs boson. But what if someone makes a discovery that fundamentally alters our understanding of the universe? Join us as we explore the shocking new finding that alters everything and about which CERN experts have just spoken. Leading particle physics at CERN, one of the top organizations in particle physics is the European Organization for Nuclear Research, or CERN. CERN, the largest particle physics laboratory in the world, was founded in 1954 and is headquartered in Marin, Switzerland. It has been instrumental in expanding our knowledge of the universe. CERN, a global center for research and discovery, was established in the years following World War II to promote scientific collaboration among European nations. The construction of the 600 mega-electron-volt synchrocyclotron, SC, CERN's initial particle accelerator, in 1957 was one of the organization's first significant achievements. Despite being small by today's standards, the SC prepared the way for CERN's revolutionary particle and nuclear physics investigations. The presence of the pion, a particle that is projected to decay into an electron and a neutrino, was first tested by scientists using the SC. They obtained the first unambiguous proof of this uncommon disintegration within hours of initiating the experiment, catapulting CERN into the international scientific limelight. CERN's focus broadened as research advanced. A period of major advances in particle physics began in 1959 when CERN unveiled the proton synchrotron, PS, a more potent accelerator that made higher energy particle interactions possible. The Isolde facility, which was built in 1967 to create and examine radioactive ions, allowed CERN to conduct even more research. Isolde became crucial for study in a number of fields, including as astrophysics, medicine, and nuclear physics. The creation of the intersecting storage rings, ISR, in the late 1960s was one of CERN's most revolutionary achievements. Hadron colliders were first created in January 1971 when the ISR collided two proton beams for the first time. The construction of future accelerators was greatly aided by this novel method, in which particles smash head-on instead of hitting a stationary target, enabling far higher energy interactions. The success of the ISR paved the way for innovative methods like stochastic cooling, which still have an impact on contemporary accelerator technology. The ISR in particular helped CERN push the limits of particle physics and transform scientific research by laying the groundwork for other programs, most notably the Large Hadron Collider, LHC. CERN's work continued to develop, building on the revolutionary successes of the ISR, which paved the way for further breakthroughs in accelerator technology. This development led to the development of the Large Hadron Collider, a far more potent and advanced device intended to explore the secrets of the cosmos in more detail. The LHC's power, one of humanity's most ambitious scientific projects, is the Large Hadron Collider, LHC, a massive device intended to unlock the universe's greatest secrets. With its enormous 27-kilometer circular ring, the LHC is the world's largest particle accelerator and is located underground at CERN. However, what is its function and why is it so important to our comprehension of the cosmos? The LHC is fundamentally a collider, a device that accelerates particles to almost the speed of light before colliding them. By simulating the conditions of the Big Bang, this approach enables researchers to reconstruct and examine the forces that formed the universe at its inception. What makes this significant? Because the laws of physics can only be discovered by comprehending the fundamental particles that control the universe. Scientists can learn more about the fundamental workings of the universe by examining the particles that are produced by these fast collisions. Two streams of highly energetic protons race in opposite directions inside the LHC, which functions as a circular tube. To be precise, these beams move at 99.999999% of the speed of light. The LHC uses an intriguing method involving radio frequency cavities to achieve these speeds. These are specialized tubes that produce alternating electric fields and are positioned all throughout the accelerator. The electric field gives a proton a slight push each time it moves through one of these cavities, increasing its speed until it approaches the speed of light. 1 can ask, why don't the protons fly off in straight lines as they accelerate? The LHC's inventiveness is on full display here. Unless acted upon by a force, protons, like other particles with an electric charge, normally travel in a straight line. The LHC employs a strong system of magnets to bend the course of these particles in order to maintain their circular motion. It looks strange at first because magnets deflect particles rather than accelerate them. So, how can magnets maintain the circular motion of these protons? The magnet's strength holds the key to the solution. Particles traveling at almost the speed of light can have their paths bent by the powerful magnets at the LHC. Strong magnetic fields produced by these magnets push and pull protons into a circular orbit. These magnetic fields have an incredible strength of 8 Tesla. The Earth's magnetic field is merely 0.04 Tesla. To put that into context, they must be in a unique superconducting condition, which enables them to function without losing any electrical energy, in order to produce such strong magnets. The temperature required to reach this superconducting state is extremely low, around -271.3 degrees Celsius. Massive detectors have been placed at 4 specific locations along the ring where the 2 proton beams converge. The magic occurs in these collisions. Hundreds of additional particles are created as the protons collide and split apart. The most fascinating discoveries can be made by scientists here. However, it's not as simple as it seems to find these particles. These collisions create short-lived particles that decay into other particles after existing for a very brief moment. CERN has constructed some of the biggest and most sophisticated detectors ever made in order to record these brief occurrences. In order to examine the characteristics of the particles produced and assist scientists in identifying unknown particles, the 2 largest detectors, ATLAS and CMS, are built to collect a variety of data from every collision. Then there is ALICE, which focuses on the study of quark-gluon plasma, a state of matter thought to have existed in the early universe shortly after the Big Bang. The last goal of the LHCb detector is to better comprehend the minute distinctions between matter and antimatter, which could provide the answer to the riddle of why there is more matter in the universe than antimatter. The core of the LHC's scientific mission consists of these 4 detectors: ATLAS, CMS, ALICE, and LHCb. When combined, they shed light on everything from the basic components of matter to the structure of spacetime itself. The LHC gathers a great deal of data from each collision in addition to accelerating particles to extremely high speeds in order to solve these puzzles. This enormous volume of data is essential for advancing our knowledge of the most important issues facing the universe and for driving discoveries like the Higgs boson. Breaking the universe. The Higgs boson is one of the most amazing findings from the LHC investigations. This mysterious particle, sometimes known as the God particle, was famously verified in 2012. It is essential to the behavior of matter since it provides mass to all other particles. However, a tremendous quantity of data processing and analysis is needed for the Higgs quest and innumerable other groundbreaking investigations. The LHC produces about 1 billion particle collisions per second, each one the true difficulty, however, is not just in gathering this data but also in sorting through it to identify the uncommon, intriguing occurrences concealed within the noise, which may potentially reveal hundreds of new particles. The variety of studies conducted at the LHC is exemplified by 2 important experiments employing ALICE and LHCb. The quark-gluon plasma, a state of matter believed to have existed shortly after the Big Bang, is the subject of ALICE research. Quarks and gluons, the basic building components of protons and neutrons prior to their binding to form the matter we know today, make up this plasma. In order to shed light on the early stages of the universe's history, ALICE seeks to replicate and investigate this primordial soup of particles. Concurrently, LHCb explores one of physics' most profound riddles: why the universe has more matter than antimatter. The Big Bang should have produced equal amounts of matter and antimatter, according to theoretical physics, yet observations reveal that matter makes up the majority of the cosmos. By identifying the minute distinctions between matter and antimatter, LHCb hopes to provide light on the reasons for the universe's formation. These experiments are not at all straightforward. Processing the massive amount of data produced by the LHC calls for complex systems. Within the detectors of the LHC, 1 billion proton collisions occur every second. Only a small portion of the many particles produced by each impact may be used for scientific examination. The detectors must be able to pick out and capture only the most significant events, because more than 99.9% of the data generated in these collisions is useless. The amount of data produced by the LHC is astounding. Approximately 1 million terabytes of data are recorded daily, which is enough to fill more than 300 contemporary 1 terabyte SSDs. However, gathering this data is just the first step. When scientists examine it and make new findings, the real work starts. It's like trying to find a needle in a haystack. For instance, in order to find the Higgs boson, scientists had to find extremely precise signals that would show the particle was there among the debris from collisions. How, then, do the LHC detectors determine what information is worthwhile to record? They use a variety of advanced technologies that are intended to track particles with remarkable accuracy. Consider one of the most intricate detectors at the LHC, the CMS experiment. It is composed of many subdetectors, each of which has a distinct function. Among these is the tracker, which monitors particle trajectories. When charged particles travel through the silicon layers that make up the tracker, traces are left behind. Scientists can determine the particle's origin and motion by using these traces to reconstruct its trajectory. The calorimeter, which gauges particle energy, is another essential subdetector. The calorimeter, which is made of lead tungstate crystals, measures the light that is released when a particle travels through it. Scientists can determine the particle's energy based on the quantity of light it produces. When combined with other detectors, the tracker and calorimeter offer crucial information about the particles created in a collision, which scientists can utilize to find possible new findings. The actual investigative job starts as soon as the data is gathered. For instance, scientists are aware that they need to search for a particular signature left by the decaying particle in order to locate the Higgs boson. Almost immediately after production, the Higgs boson decays, frequently splitting into 2 photons, or light particles. In the detectors, these photons have a distinct signature. They create a flash of light in the calorimeter but leave no trace on the tracker. But it's not easy to separate the decay photons of the Higgs boson from the numerous other photons created during the collision. The energy and direction of the photons are among the other characteristics that scientists must take into account in order to distinguish the Higgs signal from background noise. Generally speaking, the photons generated by the Higgs decay behave differently from those generated by other processes. Here, sophisticated algorithms are used to separate the Higgs signal from the vast volumes of data. When the Higgs boson was eventually discovered after decades of searching, this meticulous study paid dividends despite the task's complexity. The effort doesn't end there, though. Physics redefined every year, the LHC's experiments generate an astounding 15 petabytes of data. This amount is so large that each petabyte is the equivalent of holding 250,000 films. More than 200 petabytes of data have been collected by the LHC over the years. This wealth of information continues to inspire groundbreaking discoveries. Evidence for quarks, the basic building blocks of matter, is one of the most intriguing discoveries made possible by the LHC. These particles have many different flavors, and the way they interact is essential to the universe's structure. However, because of their enormous energy levels, many quark kinds are extremely unstable and decay into other particles fairly instantly. For example, beauty quarks have a very short existence, between 1 and 2 trillionths of a second, yet they contain a lot of information about the structure of reality. Long-held beliefs regarding quark behavior are called into question by new data from the LHC. The disintegration of quarks into particles like muons and electrons follows a particular pattern predicted by conventional physics. However, the observed probability of quarks decaying into muons differs from the expected value when compared to electrons. This disparity raises the possibility of unidentified forces at work and points to physics outside of the Standard Model. The Standard Model, which offers a framework for explaining the interactions of the most fundamental particles in the universe, has long been the cornerstone of our knowledge of particle physics. But it is not complete. 3 of the 4 fundamental forces, electromagnetic, strong nuclear, and weak nuclear, are explained by it, but gravity and the enigmatic dark matter, which is thought to make up a large portion of the universe, are not. Some scientists have theorized the presence of a new particle or force that interacts slightly with electrons and muons as a result of the anomalies in quark decay rates. They make conjectures regarding an energy carrier known as the Z boson, a particle so minuscule that it has not yet been discovered. If verified, this finding could broaden the scope of the Standard Model and offer important new information on long-standing issues about the cosmos, such as the nature of dark matter and the enigmatic function of the Higgs boson. These discoveries are not merely theoretical oddities. Rather, they could be a step in the direction of one of physics' greatest goals, the unification of the fundamental forces of existence into a coherent theory. For decades, this theory of everything has been physicists' holy grail. We might get closer to this unification and addressing discrepancies in current models if a new force or particle is discovered. The potential for such revolutionary developments highlights the significance of the LHC, which continues to be the most potent particle collider in the world. More than 10,000 researchers and contributions from hundreds of labs and institutions throughout the world are part in this global endeavor. The LHC challenges the limits of our knowledge as it works to bring the fundamental forces together with the deepest secrets of the universe are about to be revealed by scientists. This next discovery may hold the secret to solving centuries-old physicists' puzzles and provide fresh perspectives on the universe. A revolutionary finding. CERN scientists have made history by identifying high-energy neutrinos produced by the LHC for the first time. With remarkable accuracy, 53 neutrino interactions have been discovered, marking a major turning point in particle physics. This discovery promises to clarify some of the most profound cosmic phenomena, including the powerful neutrino interactions that take place in star cores and the explosive forces that propel supernovae, in addition to providing insight into the universe's most enigmatic particles. One of the universe's most elusive and mysterious particles is the neutrino. These minuscule, practically massless particles, devoid of any electric charge, are continuously moving across space and engaging in almost imperceptible interactions with matter. An estimated 100 billion neutrinos flow through each square centimeter of our body every second, but we are totally oblivious to their existence due to their spectral nature. Neutrinos are produced in a number of ways, including the fusion or disintegration of atomic nuclei, the aftermath of radioactive decay, cosmic ray interactions, and the high-energy environments of particle accelerators and nuclear reactors. Their near invisibility has led to their being dubbed ghost particles. Even naturally occurring processes, such as the breakdown of potassium in bananas, produce them. Neutrinos are widely distributed, yet because of their poor interaction with matter, they are notoriously challenging to investigate. Therefore, it takes extremely advanced and accurate technology to detect them. Since the initial discovery of these elusive particles in 1956, when they were seen escaping from a nuclear reactor, scientists have been searching for them for decades. In 2021, scientists discovered 6 neutrino interactions, offering the first conclusive proof of their existence in a collider experiment. 2 additional years of meticulous investigation and data gathering were necessary to verify their existence. Nevertheless, this finding is a huge step forward, said James Boyd, a particle physicist at CERN and co-spokesman for the Phaser project. Ghost particles can teach us about deep space in ways that other methods cannot, he said. The discovery of high-energy neutrinos at the LHC is especially intriguing since it creates new avenues for research into the most extreme settings in the cosmos. Understanding some of the most fascinating facets of particle astrophysics, such how stars burn and burst in supernovae, releasing enormous quantities of energy and neutrinos in the process, may be made possible by these high-energy neutrinos. Additionally, neutrinos might provide light on the enigmatic operations of black holes and other celestial phenomena that we presently only speculate about. The scientific community is already excited about the initiative, which will keep gathering data until the end of 2025. Physicists anticipate discovering novel and surprising results when more neutrino interactions are found, which could put our knowledge of the cosmos to the test. With every new finding, they get one step closer to solving the enigmas surrounding these spectral particles and, consequently, the underlying forces that form the universe. In the years to come, neutrinos may prove to be essential messengers in the pursuit of answers to the most profound queries concerning the beginnings and mechanisms of our cosmos. It's time for the subscriber pick of the day. Dr. Elena Hartman stood in front of the control panels in the center of the CERN laboratory, her fingers shaking a little as she went over the data. Something strange had been found deep inside the Large Hadron Collider for weeks. In the streams of data, a particle unlike anything they had ever seen had emerged, flickering in and out of existence with a sudden intensity that was unanticipated. Nobody was able to explain it. As she stared at the flashing screen, she muttered, "Could it be?" The enigmatic particle had displayed characteristics that went against every known physics law. It was more than just a novel particle. It appeared to have unanticipated interactions with gravity. CERN rapidly became aware of the anomaly. Working around the clock, the team collected data, ran simulations, and double-checked their results. Soon, news spread that scientists at CERN were about to make a discovery that would change the universe's laws. Then, a few hours earlier, Dr. Michael Adler, the principal physicist, sent a message to Dr. Hartman requesting an urgent news conference. The message was clear. Scientists at CERN had finally spoken out about the terrifying new finding that will forever alter the course of history. The particle they discovered was proof of a parallel universe with drastically different physics rules, not merely a bug in the system. They asserted that this finding might provide the solution to comprehending the fundamental structure of existence. Elena wondered, while the world listened, what this meant for the future of humanity. Outside of CERN, however, a different form of speculation, the web of conspiracy, was rife as the scientific community rejoiced over the revolutionary finding of a parallel universe. Conspiracy theories have long been drawn to the LHC. The idea that the LHC would produce a black hole so enormous that it would eventually bring down the Earth was one of the first and most well-known conspiracy theories about it. The concept was based on the assumption that a small singularity may be produced in some way by colliding particles at almost the speed of light. But in spite of these worries, no such calamity has happened. Since the creation of a hazardous black hole seemed unlikely, if not impossible, CERN experts spent years assuring the public that their research was completely safe despite the rumors. These guarantees, however, had little effect on conspiracy theorists' imaginations. A particularly strange theory surfaced in the early 2000s as CERN's groundbreaking experiment encountered delays and difficulties. Some hypothesized that sabotage, intentional meddling by a future time traveler, was the cause of the LHC's malfunctions. This idea suggests that the time traveler was frantically trying to prevent the collider from working out of concern that its activation would have devastating results. The bizarre aspect of the tale concerned a time-traveling bird that was allegedly involved in the sabotage attempts and was allegedly carrying a baguette. The fundamental tenet of the hypothesis that the LHC's power was so great that it could be the cause of a catastrophic event remained at the center of numerous conspiracy theories, even though the specifics of the theory were undoubtedly absurd. However, there are many other wacky theories concerning the LHC than time travel. According to a different, possibly more well-known idea, CERN is covertly creating portals to other dimensions or even hell. Following CERN's announcement that it was experimenting with producing small black holes in an effort to explore antimatter, These hypotheses gained popularity. Those who were concerned about the possible risks of establishing portals to distant regions or parallel universes were alarmed by the notion of producing black holes, especially on such a small scale. The next frontier in particle physics, which builds on the legacy of the LHC, promises to provide even more profound answers to the enigmatic components and origins of the cosmos. Although the 2012 discovery of the Higgs boson was a huge advancement in particle physics, it also raised a number of unanswered issues. How did it influence the basic forces and matter that we see around us today? Furthermore, can the enigmatic imbalance between matter and antimatter or phenomena like dark matter be explained by this elusive particle? This new frontier is what the Future Circular Collider, FCC, seeks to investigate. The FCC, which will replace the LHC, is expected to advance human knowledge by providing hitherto unheard of levels of precision and energy. Scientists are closely examining every aspect of the FCC feasibility study, from the financial and technological obstacles to the effects on the environment. Could studies conducted at CERN hold the secret to solving the puzzles of dark matter, the universe's beginnings, and the underlying forces that control everything in our environment? Please share your thoughts in the comments section below.